Hey guys, hope everybody's doing okay. What we're going to do right now is take a look at a bunch of acidic substances and compare their strengths. So acids are basically broken up into two categories where we have binary acids. Binary meaning two things. All right. So examples of this would be something very familiar, like HCl, hydrochloric acid. H2S, a little less familiar, but hydrosulfuric acid. We also have acidic substances that are called oxoacids. So we're familiar with these two. Something like carbonic acid, H2CO3, and nitric acid, HNO3. Right? So these are your oxoacids or oxyacids, and you have your binary acids like HCl or H2S. We have way more oxoacids because there's all sorts of options with the number of oxygens you can have. We have more limited options with the binary, so there's really not too many of those we have to worry about. But there are a lot of oxoacids we have to worry about because we could change the number of oxygens, and make HNO3 into, it could be HNO4, HNO2. You have a bunch of different options here to look at. We're going to wrap up the lesson towards the end looking at bases for just a couple minutes, but we're going to spend most of our time today on acidic substances. So let's figure out which acids are the strongest when we have to compare a group of them. These are our four categories we're going to focus on, like I already said. The main thing you need to know here is the definition of an acid. So if you know the definition of an acid and you could think through things a little bit, this actually becomes a pretty easy task to handle. So back from our, really back from Chem 1, in our review here from Chem 1, acids donate a hydrogen or a proton, right? Acids are proton donors. It goes back to our basic definition of what an acid is. So strong acids are excellent proton donors. Weak acids are poor proton donors. So all you want to do here is ask yourself, is it easy or hard for my acid to donate a hydrogen? The easier it is to donate a hydrogen, the stronger it's going to be. The harder it is to donate a hydrogen, the weaker it's going to be. Easy. So we set to compare acids within the same period. It's in the same row of a periodic table. We're going to compare binary acids in the same group, which is up and down a column. Okay? So let's take a look at those first, and then we'll move on to oxyacids for our last two categories. So we're going to start with binary acids in the same period or row of the periodic table. So you can see I'm just picking a random period here. We have period 3. We have SiH4, which you wouldn't really think of as being acidic, but technically it could be. pH3, H2S, and HCl. All right? So we already have the strengths of them on the screen here, but let's figure out why HCl is a strong acid and SiH4 is a very weak acid. We already know from memorizing our 7 strong acids that HCl is one of those top 7. So let's see why. Within a period, the bond length is approximately equal. So I know that the bond length isn't exactly equal here. Like I know as you go from left to right across the periodic table, the bond length decreases because of that higher coulombic attraction, higher nuclear charge of chlorine compared to silicon, right? So the HCl bond here is a little bit shorter than the SiH4 bond, but it's basically negligible because all of these are in period 3. So silicon, phosphorus, sulfur, and chlorine all have their valence electrons in the 3rd energy level. All right? So if we can't really focus on bond length here within a row, we have to focus on something else, which is electronegativity. So the more electronegative an atom is, the more it wants an electron. We know that from Chem 1 and from Unit 1. What does this do then? This weakens the bond to the hydrogen. What does that mean? Well, that means the hydrogen can be donated easier, which means what? Stronger acid. All right? So if you're going to compare HCl, all right, take a look at that. You're going to compare that to H2S. Draw that real quick. Okay, bond length here. Okay, the bond length here, about the same. Okay, I know the bond length for HCl is a little shorter, but again, it's like a negligible difference here. Since the bond length is about the same, we have to look at electronegativity. So you know that chlorine has a higher electronegativity than sulfur does. Chlorine's one of the top three, all right? It's in that halogen group, so it wants electrons pretty bad. What does that mean then? It means the chlorine wants the electrons in this bond here, okay? It wants them a little bit more than the sulfur wants the electrons in this bond, because chlorine has a higher electronegativity. Well, if chlorine is trying to hog these electrons from this bond, that actually weakens the HCl bond, right? If chlorine wants them, hydrogen can't have them, right? So it allows this bond to break a little bit easier and allows the hydrogen to be donated, all right? Here, with H2S, hydrosulfuric acid, this bond, like sulfur doesn't want the electrons in this bond as much as chlorine does, right? So it's not really pulling them over here as much. So hydrogen could like hold on to them along with sulfur, and it could, like, this bond will remain intact a little bit better than the HCl bond will. So it's not as easy to break this bond right here and have the hydrogen be donated. That's why HCl is stronger than H2S. Same thing with, phosphorus here. Phosphorus has even lower electronegativity than sulfur, and silicon even lower electronegativity than phosphorus. So for SiH4, it's very covalent in structure there, okay? So very little electronegativity difference here, very equal sharing between silicon and hydrogen for those bonds, right? Which doesn't allow the hydrogen to be donated easy at all. All right, so across a row, you want to think about bond length, it being approximately the same. So you focus on electronegativity, and the atom that wants the electrons more will hog them a little bit more, allowing hydrogen to break off and be donated a little bit easier. All right, so left to right, acid strength increases. A good way to remember this is if you know your 7 strong acids, you know that HCl is one of the 7 strong acids, and none of these other ones are. So if you have to compare binary acids in the same row, you know it's going to be stronger as you go towards the right, because that's where one of your 7 strong acids is. You need to know how to explain it, though, and it has to do with electronegativity and the weakening of the H whatever bond to allow that hydrogen to be donated. Okay, let's look at binary acids in the same group. This is a little bit easier to understand, I think. We're looking at the halogen group here, so we have HF, HCl, and then we'd have HBr and HI underneath that. Bond length increase is going down a group pretty substantially because you have a difference in energy level. So HF, fluorine's in energy level 2, HCl, Cl is in energy level 3. Okay? So what does this do as you go down a group then? The longer bond length between HCl and HF, the longer bond length for HCl, is going to weaken the Coulombic attraction between that element and hydrogen, allowing the hydrogen to be dissociated easier. So really easy to think this through. Again, we want the hydrogen to be donated. We want the bond between hydrogen and something else to be weak so that hydrogen can be donated. Of course, a longer bond length is going to be a weaker bond, right? Then the H could dissociate or be donated a lot easier. So we have HF right here, and then we have HCl. A little more drastic there. So Cl is further away from H because Cl has 3 levels of electrons. Okay, 1, 2, 3. And fluorine only has 2 levels of electrons. All right, so this is a weaker bond right here between HCl than HF. So the longer the bond length, the weaker the Coulombic attraction, the stronger the acid, because for HCl, since this is a longer bond, right, longer bond length, and therefore a weaker Coulombic attraction because it's further away, this hydrogen could break, okay, and dissociate easier or be donated easier to something else compared to HF. All right, so pretty simple. Longer bond length, stronger the acid is going to be due to a weakened Coulombic attraction. Going down that column, you have HBr. That's one of our 7 strong acids. And we have HI. Okay, so we have HCl, HBr, HI, and a couple other strong acids. Br is in level 4, HI, so iodine is in level 5. So of these acids in the halogen group, of these binary acids, HI would be the strongest. HF would be the weakest. All right, guys, so that takes care of, all that. Let's move on to oxyacids to wrap this up here. And then we'll talk about bases for just a couple minutes. So you need to be familiar with this functional group. This is a carboxyl group. The R stands for just some other carbon stuff. Right? It could be a long chain or a shorter chain, just some other elements. And you have your C double bond O, single bond OH. Now students see the OH group here and they think of a base. And that's true if you have something like NaOH. All right, but it's not true when you have something like this with this carboxyl group. So the OH is bonded to a carbon group here, all right, and not some other metal. So it's not going to be basic. It's going to be an acidic hydrogen. So if you're looking at this, acids are proton donors, hydrogen donors. Here's your hydrogen. You want to ask yourself, how can this hydrogen be donated, right? How could that be donated to something else? It could be donated to something else if it has a weaker bond between the hydrogen and the oxygen, all right? So you want to ask yourself with oxyacids, how easy is it for this acidic hydrogen to be donated? The easier it can be donated, the stronger the acid is going to be. So let's take a look at a couple examples here. These are all common carboxyl groups. So acetic acid is vinegar. You can see that it's acidic because of that carboxyl group. Citric acid, in different juices, you have a bunch of carboxyl groups on that actually. Aspirin, right, another carboxyl group here. Right, benzoic acid, benzene ring plus carboxyl group. Right, so you can see all those carboxyl groups there, making these things acidic. So we're going to compare oxyacids with the same number of oxygens first. So the higher the electronegativity of the central atom, the stronger the acid is going to be. So we're back to electronegativity here. I'm going to try to introduce something new here, a new vocab term called the inductive effect. All right, I'll explain it a little bit more on the next slide. But an inductive effect is when one atom has an effect on other atoms a couple bonds away. All right, so a highly electronegative atom affecting bond polarity 2 or 3 bonds away is what we're focusing on here for oxyacids with the same number of oxygens. A highly electronegative central atom weakens the hydrogen bond a couple bonds away, allowing it to be donated easier, right? So let me go back a little bit here and show you kind of what I'm talking about. Erase some of this. All right. This is what we're considering our central atom. Okay, now it's not always carbon. If you have nitric acid, it's HNO3. It would be nitrogen that we're talking about for your central atom. But the electronegativity of this central atom, okay, that affects this bond right here, okay? The electronegativity of carbon, or whatever it is, affects how strongly this hydrogen is bonded to oxygen. If this has a really high electronegativity, it's pulling it's like trying to pull electrons in from everywhere, right? So if it's pulling electrons in from everywhere, it weakens this bond right there, okay? Allowing the hydrogen to be dissociated and donated easier. Okay, so let's take a look at it in a couple examples here. We're going to look at 2 simple like weaker acids here. We have HClO, right? HClO and HIO. Right, with those 2 acids. You recognize them as oxyacids because it's not binary, obviously. And it has an oxygen, so it has to be an oxyacid. So they have the same number of oxygens. Each of these have 1 oxygen. So you have to look at electronegativity difference of the central atom to compare. So we're going to compare chlorine with iodine. All right, it has it right here in the slide. Electronegativity of chlorine is a 3. Electronegativity of iodine is a 2.5. Chlorine's more electronegative. Look what happens. chlorine, being more electronegative, is pulling electrons in towards it. A little bit more than the iodine is. It's called electron drift. See that right there on the slide? If the electron drift is occurring towards chlorine, more so here, it allows this hydrogen to dissociate and to break off and to be donated easier. Okay? Iodine doesn't have as high of electronegativity. It's not causing as much electron drift. So the H is bonded to that oxygen with a little bit stronger bond here. So you can see that they both have that hydrogen dissociate. Look at the Ka value though for HClO. 3 times 10 to the negative 8th. Still pretty weak acid. But compared to HIO, look at the Ka value. 2.3 times 10 to the negative 11th. Way weaker. This is a way smaller Ka value. Remember, the larger the Ka value, the stronger the acid is. So comparing these two, same number of oxygen, higher electronegativity means stronger the acid is going to be, right? Because it pulls the electrons in, weakens that HO bond a couple bonds away. All right? Let's take a look at it, though, with a different number of oxygens. Now, remember, oxygen is really electronegative itself, all right? That's why we went here. Like, why can't we focus on the oxygen? Well, oxygen's really electronegative, and there's only one here and one here, so they kind of cancel out. But if you have something like this, or we're going to look at hypochlorous acid versus perchloric acid, the central atom remains the same, chlorine, right? But look at the difference here with number of oxygens. Okay, it's increasing as you go towards perchloric acid. So, being electronegative, the more oxygen atoms bonded to the central atom, the stronger the acid is going to be. So it's also due to the inductive effect. There's way more electronegativity all around the central atom here. So let's take a look at it. The very electronegative oxygen atoms weaken the bond between hydrogen and the other atom. That strengthens the acid. So it also goes back to, how do we weaken this HO bond? Okay, how do we weaken that so the hydrogen could dissociate and be donated easier? You've got hypochlorous acid, you have one oxygen there, okay, so you want the hydrogen-oxygen bond to be weak. It's not very weak at all. Its Ka is 3 times 10 to the negative 8th. Look at chlorous acid. This oxygen's over here now, right? You have another oxygen right here, pulling, you have one here too. These oxygens here, pulling electrons in, weakens this bond, so the hydrogen could dissociate and be donated. Look over here, 3 oxygens, all pulling in pretty strongly on electrons, weakens that bond even more, right? Look at this, 4 for perchloric, 4 oxygens, lots of electron pull here, weakens that even more, all right? So chloric and perchloric are considered strong acids. So the Ka value, see how it's not listed? Ka is like, bazillion. Okay, it's way bigger than 1. Look at these other two. Hypochlorous and chlorous are relatively weak, very small Ka values here, because there's not as many oxygens around the central atom there. All right, so the more oxygen you have, then the greater the inductive effect is, and therefore the acid strength is stronger. And that's the one on your note sheet here. I'm looking at the note sheet real quick. I went back here, and if we went back to the oxoacids with the same number of oxygen, there is one on your note sheet that we had to compare in addition to this one here, and that's H2SO4 versus HClO4. Okay, so you want to compare those two. Both of these have the same number of oxygens. Right? So we go to electronegativity, and which electronegativity is higher. Chlorine has a higher electronegativity than sulfur does. So HClO4 would be the stronger acid here compared to H2SO4. Because chlorine has a higher electronegativity than sulfur does. All right? So I just noticed that real quick. Want to go back, so you have your note sheet complete. Okay, so to summarize here, the sheet in your packet is actually the note sheet you took today is the summary for all of this. It's a really nice, neat summary of all these 4 categories here. you may or may not have done a group activity acid strength POGIL the day before this or before this, depends on what school you were in. And this is the summary lecture for after that. So it's all pretty summarized for you already, but if you're looking at these 4 categories, binary acids in the same period, okay, you have to focus on what here? You got to focus on electronegativity. All right. Binary acids in the same group, you're focusing on bond length, because there's such a big difference in the size of the bond here going down a group. Oxoacids with the same number of oxygen, you're focusing on electronegativity. And then oxoacids with a different number of oxygens, you're focusing on the number of oxygen. So you have to know what to focus on here. Same period, electronegativity. Oxoacids, same number of oxygens, electronegativity. Same group, bond length, different number of oxygens, focus on the number of oxygen. Okay? If you can remember this, acids donate a hydrogen ion, then that is going to be key here. So you need to just figure out how can a hydrogen ion, how can a hydrogen or a proton be donated easier? Once you figure that out, you know that is your stronger acid, the one that can donate the hydrogen better. Okay, real quick on the next page of your notes, we have strengths of bases. We're going to knock this out really fast here. Here's some common bases on the slide here. What you notice is you have a nitrogen with a lone pair with some other stuff attached to it. All right? So that's one of the things we're going to look at here. If you can identify a base, you want to look at your Lewis dot structure, and you want to generally find a lone pair on a nitrogen. So bases usually have an unshared electron pair attracts a proton. So these electrons here, this lone pair on nitrogen, they're negative, right? If you have a hydrogen hanging out somewhere, that H+1 will obviously be attracted to this negative group of electrons on nitrogen. All right, so since it attracts that proton, right, proton acceptor, you're going to have something that's basic. So here's what you need to know. You need to identify your strong bases. This is really important to memorize this. All right, 2 categories, strong and weak, obviously. Strong bases are water-soluble compounds containing hydroxide. All right, so this is when your hydroxide is attracted to or part of a group 1 or group 2 metal, right? So these are more ionic looking, right? So you have something like NaOH, okay, commonly found in Drano, all right? So very strong base. Another one, you have CaOH2, right? Calcium's from group 2. So group 1, group 2 metals attached to a hydroxide ion are going to be your strong bases. They dissociate like this. So KOH, really strong base, also in Drano, or different brands of drain cleaner. KOH dissociates into K+1, OH-1, right? So it breaks, it dissociates and creates that hydroxide ion. Weak bases are where you have something like MOH, some metal attached to hydroxide. That's not group 1 or 2. So something like aluminum hydroxide, AlOH3. This doesn't dissociate very well, okay? So like the KB value here, or KSP, whatever, it's going to be really, 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 really small. All right? Here, your K values are pretty big because they dissociate very easily and nicely. Something else you want to look for is a nitrogen atom with an unshared pair of electrons, like NH3. So you can see we have an amine group, basically is what that's called, one of our functional groups. All right, nitrogen lone pair attached to some other stuff. This R could be, you know, whatever, it could be something else, right? Some other carbon group, whatever. Okay, so you need to know your strong acids, you have your top 7, and you need to know how to identify what acid is stronger when you compare them. You also need to know what your strong bases are going to be. So those need to be committed to memory sooner than later. And once you do that, you'll be good to go. All right. So strong bases, group 1 or group 2 OH, group 1 or group 2 metals attached to OH. Weak bases, everything else. And I have a couple other quick slides here. So you can see your CH3 NH2 methylamine group. Here's your nitrogen with your lone pair on it. Here's water, has a hydrogen. and you can see the lone pair binds to that H+, so that H+ ends up going here. You can see it here in the structure. You create a hydroxide, so that's a base too, right? And you have your NH3 group at the end of what you end up with here. Something like this, is it an acid or a base? Well, it could be both, because you have a carboxyl group right here. So there's your acidic hydrogen that could be donated, right? And you have your amine group here, your nitrogen with the lone pair, where you can have an H being attracted to that, which is a base, right? So this could behave as an acid or a base. You have an acidic end and a basic end of this structure. Okay, that should, yep, there we go. That should take care of the lecture here for today. So, a couple practice problems in your packet. They might be assigned today or a different day, but that'll be announced for you. All right, guys, takes care today. Thanks.